I can even go further. Like, I will say that, like, in some ways, deep learning revolution is the worst thing that happened to causal inference. In some sense, the code is God, because it doesn't matter what you described in your methods section and like how well you describe it or not. The code is very definitive about what it does and how it does it. They don't respect the data generating process. It's ineffective. It's a waste of money to gather all that data, but not to analyze it properly. And it's also, I think it's disrespectful to the patients. So I think the hardest part for like machine learning researchers going to causal inference is...
Hey, Causal Bandits. Welcome to the Causal Bandits podcast, the best podcast on causality and machine learning on the internet.
Today we're traveling to Tel Aviv to meet our guest. Before starting his adventure with computation and causal inference, he used to be a bass player. He believes in the power of good code and loves to play music with his children. Creator of CausalLib and research staff member at IBM Research. Ladies and gentlemen, please welcome Mr. Ehud Karavani. Let me pass it to your host, Alex Molak.
Ladies and gentlemen, please welcome Mr. Ehud Karavani.
All right. Thank you. Thank you for having me. I'm grateful for that.
Welcome to the podcast, Ehud.
Thank you for having me again. Yeah.
Before you started your journey with causal inference, you used to be a bass player. What is one or two experiences that you had, or one or two skills that you learned during your music career that translated to something unique about you as a researcher in causality?
That's an excellent question. So I think Ed Young, he was the science journalist for The Atlantic once. He had a piece about like the irrelevance of Nobel Prize. And he wrote like that science is the teamiest of team sports. And I think there's something about being a musician that prepares you for that. Especially if you're a bass player, like that takes like a certain character that I guess like, I don't know, give you appreciation like for good foundations, having like building a flow that will carry others, moving them forward, like, being a basis they can build on. And yeah, I mean, it all exists in music, being a part of like a greater thing and let others build on top of you and provide those foundations. I think that the leap from that to science is quite small in order to collaborate well in science, because in order to make good science, like you can no longer be a lone thinker. Like,
what's good science?
I think good science is trustworthy science. It's science that we know can generalize, and we can look at its internal and realize whether it is made up of nothing or it has some substance in it. Good science is science that is communicated properly and well to others. I mean, a scientific discovery worth nothing if others don't know about it. Like, a person can discover tomorrow like what happened before the Big Bang, but if it doesn't tell anyone else, it's worthless. And so communicating is really important for science, and so that's the presentation part, but we don't want to put like a lipstick on a pig, right? So like the essence itself should also be trustworthy. And so good science is open, and it's transparent science.
Mm-hmm. When we think about causal models, especially when we talk about them with people who are new to causal modeling, and maybe they come from more traditional machine learning or data science backgrounds, those people will often ask questions, wow, but how can we evaluate those models? In CausalLib that you created, there is a module that is dedicated to model validation or model evaluation. What was the idea behind creating this module? What was the motivation behind it?
the biggest thing that differentiates machine learning prediction from causal inference, I guess, like it's, or at least one of those, is like the fundamental problem of causal inference, right? The fact that you never have ground truth labels, so like you can never truly evaluate whether your model works, I guess.
In a direct way.
In a direct way, yes. It's not like you could generate like an area under the curve and say like it's 0.8, it's 0.7, it's trustworthy or not. In order to convince people that your model works, you need to market it. It's not just a matter of like showing some numbers and convincing. And even if people are aware of like machine learning evaluations, then they will expect that. And so you need to counter that in advance. And so CausalLib, the evaluation module in CausalLib really was raised by that need, but us needing to convince stakeholders that the modeling process that we did was okay. So first of all, it's graphical. There are like many plots with many flavors and colors. You need to make the presentation compelling in order to market it properly. And only later did we like converted these graphical visual insights into like numeric values to enable like users to do like automatic selections or selection of models based on those ideas.
What are the sub-models of this model?
Give us like a bird's eye view.
Yeah, so CausalLib generally like it has like its main components are maybe like an estimation module, which has like a lot of the more common models that we work with, like IPW or an S-learner, which is named standardization at the time, and a T-learner or like, which is like stratified standardizations. CausalLib goes way back, like it goes like before the Kunzel paper with those
2019.
Yeah, with those naming conventions. So like I had to make those up. And so it has like this estimation module, and it also has a survival estimation module for survival time to event analysis. And it also has the evaluation module, which again like is comprised of graphical evaluations. It basically tries to replicate scikit-learn structure. So it has like a metrics module with scores that are like compatible in some way, which you can like put inside like other components, like a grid search or a half space or helping space search objects. It has like a feature selection module. Again, like it tries to mirror scikit-learn. So it has like a feature selection module with like confounder selection specific methods. And it also has a contrib module, which as well as scikit-learn, like it has like slightly more maybe state-of-the-art models or models that has been contributed like not by the core team. So like might not be as tested or that, but like might be interested for users to play with.
You created at least the first version of CausalLib essentially alone, which is, well, I think it's a great challenge and a great achievement. I really admire this.
Thank you.
How was your journey with this library, and how did it start?
It started when I joined IBM Research. So I joined the machine learning for healthcare and life science group. When I joined, the people already knew they needed causal inference methods in order to answer the questions that interest them. And so, like when I first like opened my mailbox, there's I don't know if people know, but when you start a position in a corporate, like you open the mailbox, there's lots of like onboarding spam, and also like just regular spam. But there was like one non-automated email that I received, and which was my mentor, Ishai Shimoni, with like a single hyperlink in it to the Hernan and Robin's book. Today it's called What If. Back then it didn't really have a name. It was the Causal Inference book. Mm-hmm. And when I joined, since the team already had some previous projects doing causal inference, there were some fragments of code. Like each project had like maybe the one project like needed an IPW and another one needed like a Nest learner, and so it was scattered around. And like when a new project came along, like people would maybe copy paste those files, maybe tweak them a little bit, but there was nothing like coherent about it. And then I came along as a student in a student position, and I don't know, like maybe partly because like maybe coding is like donkey work, maybe because I had some basic immature sense about like how important it is to build like tools for others to use. Maybe it was just like, maybe it was just a vacuum I came in and filled. But I started like organizing those fragments into one consistent, coherent Python package with like with a reasonable API. Like I broke down the code because like it was all jangled up together. So like I broke it down to like a nice scikit-learn like API, and I combined like I combined fractions like from all over the place in order to create like a library that will have causal inference methods like for causal estimation that could be passed around a project, not even passed around, like be installed like any other tool that like we use. And that was like the internal beginning of CausalLib, probably like, I don't know, like maybe early 2017. And then like once we realized that's like after some like internal tests and uses like in projects that we have, I guess like I realized that this is like something that can be useful to other people as well, to many more people. And those are the early days, like those are like 2017 again. So like do Y looks very different from today's do Y. Causal ML is non-existing, I think. Econ ML is maybe around, but like the most advanced methods that Econ ML currently has, like the papers weren't out yet back in 2017, so it probably looked quite different than now. And so I had this idea that like we will
open source it. It was a new idea.
And we had some, and it required some like uphill battles, like fighting corporate bureaucracy and corporate politics. And I was a student, like I was not acquainted with corporate politics. I had nothing to do with it. And lucky for me, my mentor, Ishai, like he had my back. And we went along with it, and we thought, and we were able to publish it and make it available for everyone to use. And that's how we started.
How was your experience starting in a field like causality so early in 2017? I mean, as you mentioned, many of the papers for the methods that today are considered being like classics, like double machine learning or some other methods, they were not even out there. And the idea about causal machine learning was something that was still incredibly niche. Maybe a year or 2 years later, it started building more momentum with the Book of Y as well. Mm-hmm. But that was the very, very beginning of modern causal inference and machine learning. So how was your experience? How did you feel back then?
It was tough. In the sense that, as you say, I think there was like relatively few materials available. So as I said, like I got the Hernan and Robbins book, but that's a hard book to start with. Like, I don't know how other people learn, but like that book is so full of, it's an excellent book. It's full of details. I regularly go back to it to like relearn things and like get a better understanding, but that's not, I think, like a good first book in some sense. I prefer, I don't know, my learnings, like starting from a bird's eye view and drilling down and not getting into the math and the details very early. It's easier to conceptualize like abstractions, like when you look at the bigger picture before then like drilling down to the details. So like resources were limited in that sense. Like you needed to work harder in order to learn, in order to get the intuition, in order to fully grasp like not what the math looks like, but like what it actually does. Like, I don't know, like what IPW really does, like what standardization really does, like how does it balances, how does it allows us to obtain causal effect. So and also like in terms of resources, they were not like digitized, and so there was no code. Like I like code because like code is very direct in what it does. I mean there are no second guesses. It does what it does, and there were like, I don't know if but like very little available code resources that like will allow you to see like what's actually happening within those models, how things are actually being done, how they are actually being implemented. But I think like nowadays is much better. Like we have more software, we have more books written for like varying audience, for probably more computer science, machine learning people, for like more for econometricians or epidemiologists. So yeah, so we are definitely in better shape now. It was slightly harder at the start, I guess, but people had to struggle as well in order to make the resources that are today that exist today.
What do you think we as a community should do today in order to make causal inference and causal machine learning, causal AI, even more accessible to broader public than it is today?
That's a good question. I mean, so we just established that like we already have like the learning resources piling up, and we have excellent software by now. We have excellent software that like given data metrics of covariates and treatments and outcome will spit out causal effects, and it will do it nicely. However, I guess like as every practitioners will probably know, getting data to look as metrics of covariates and treatment and outcome is a complex process. It takes as much knowledge in causality to organize data to be ready for a causal inference analysis as it is to develop methods and apply causal inference methods. You need to know like what covariate you need to choose to adjust for. You need them to take them at a specific point in time, like they need to be like before the treatment happens, they can be like after the treatment happens. The outcome, you need to establish the follow-up time, you need to establish a time zero. All those things are complex to all those things are like quite complex to implement using like databases, queries, and data processing. And I think a solution that will make it easier will be will provide like a great leap in order to make causal inference easier. A solution that will allow you to take a database, like an event-like databases, because I mean, no one curates data for research, for like I don't know, unless like you're a research lab that like generates your own data. I worked with insurance claims data or electronic health records. I don't know, like marketing people work with like events, like website events and interactions. Banking, finance people work like with banking databases. Like all those databases were not created with research in mind. They have like they fulfill like a relatively different need.
A different purpose in mind?
Yeah, a different purpose in mind in the sense that they might be used for audits or for a different task entirely. They will and we repurpose them for research. And practitioners who do that, who use like observational data, probably know how difficult it is to take the data that it's out there and make it and fit it in a causal analysis. And so I think a solution that will make this process slightly more automated will be more beneficial than like another causal inference methodology package or something like that. Yes.
Mm-hmm. So what you say is that you feel that we are actually missing tools before this preparation phase, where we can take data that was recorded maybe just for, with some other idea in mind, some other goal in mind, and repurpose this data or reshape this data in a way that is that can be consumed by causal inference machinery that we already have.
Yeah, definitely. That's the point. Yes.
You mentioned electronic health records, and health projects is something that you worked on, like practical applied projects around health at IBM Research. What are some of the main learnings, main insights you got from this stream of your work? Let me give you an
Context. Many people are fairly interested in
understanding what is needed in order to make a actual real world causal inference or causal machine learning project. What are the intricacies? What to pay attention to when we are in a preparation phase for a project like this? So for many people who are just starting with causality, they don't have too much practical experience. They are very curious about this stuff. Like, how do you look at the data? How do you communicate with the stakeholders, and so on and so on. So if there are any insights that you think could be valuable for the community, I'm pretty confident that people will be very, very grateful for them.
Yeah,
so I think like the first and foremost,
what you need to understand is the domain. And for that, you don't even need data. It's the work that you need to do is before you even take a look at the data. It's when you try to realize what data you even need. And so it revolves interviewing the domain experts. Like in our case, it's probably like doctors and physicians, to set up the problem, to know like what questions do they want to answer, what's the problems, what's the complexities in answering those questions. All of those can guide you to know what data you want to collect, like what's the estimate you want to estimate. And extracting that knowledge from domain experts is hard. You need to take their knowledge and somehow fit it in to, I don't know, to a directed acyclic graph in some sense, right? You need to distill their knowledge to make something sensible for a causal analysis. And so, for example, like I think after lots of trial and error, like we realized that like especially physicians, they know the process of treatment decision much better than they know the process of outcome, of what determines an outcome, because they prescribe the drugs, for example. So like they know like what patient would receive like what drugs, relatively speaking, and they know where the fuzziness exists, which we need to take advantage of in modeling, because like if there are strict guidelines that like everyone adheres to, like you have no place to operate within and make causal claims, because I know it's like it's that will be like an overlap issues, right? You have no variance to start with. Yes, thank you. So we realized that like modeling the decision to treat is much simpler than modeling whatever determinants of the outcome may be. And so that's a slow process of interviewing and figuring out the complexities, because they will start and tell you, oh, but those kind of patients, like they will get something different. So that's a covariate you need to adjust for.
What is the best part of working with physicians and people who are so deeply ingrained in the domain?
Their passion. They come to us because they have problems that they really seek to solve. It's a strong driver for doing good work.
You worked on many interesting projects in your career. Some of them were involving topics like child delivery. You also work with people who are interested in causal effects related to surgical, in medical sense, surgical interventions. What were the main lessons from those projects, and looking at something so close to human body and human life?
So I studied computational biology in university because I had a vague knowledge about computers, and I know they can be a great tool, but I was not interested in the tool itself. I was interested in what it can do. And biology seemed like a very straightforward domain to do good in, I don't know, like quote unquote good. As I evolved my career, like I moved from biology to more applied biology, right, to medicine and human health more directly. And so if you work on human health, it's a very direct way to improve people's life. I mean, there can be lots of other ways that you can improve lives in a very indirect way. This is what basic research is always about, right? Like no one thought we will discover CRISPR. They just like studied somehow microbiome, how bacteria fights against viruses. It's like very basic science, but it ended up being so meaningful. I didn't have the patience. I want to do something slightly more direct, and so working directly in healthcare seemed like the right opportunity to do that.
What are the main challenges in working with practitioners, from your point of view as a scientist or researcher?
First of all, as we said before, is like closing the gap, like trying to extract knowledge from them is a very communication heavy, like interaction heavy. It's a communication heavy interaction that you need to carefully listen and like carefully convey, and then try to distill what they say in natural language and distill that into a DAG. The second thing I think is hard is the disappointment. Because they are not statisticians and they are not causal inference experts. And so their worldview is based on things they hear from like a pop media or popular science in some sense. And they come to you and they want and they heard that causal inference is important and it now can be done and so exciting, and they're hyped about it. And they come to you and they want you to use the tool. Like they heard machine learning, they heard about deep learning, they might even know PyTorch or something like that. And they come to you and they say like, oh, you have this CausalLib tool, come on, let's fire it up and let's get some causal effects. And then you sit down and you start to talk about estimates and causal gaps and a causal roadmap and target trial emulation and I don't know, time zero and self-inflicted biases, and they are baffled. You can like you can see how less engaged they become as you speak. They came for an answer for a tool and they get a teaching session in some sense.
It's like in life in general.
Yeah, isn't it? Yeah. You want the easy solution and you get more homework in some sense, and then they become upset. Because they realize, I don't know where I read it before, but they realize that causal inference is a bait and switch scheme. Because we speak so highly about the importance of causality, and we say that counterfactual prediction is so important, and that's the way that we need to operate. And yet, when we provide the tools, we provide a regression model. We provide we provide like regular machine learning models or regression models. And we tell them that if they think hard enough and careful enough, it will become causal. And that sounds like snake oil. That sounds like a self-help book, like the bad kind. Like the secret was in you this whole time.
Well, sometimes it is, I guess.
Sometimes it is. I can even go further. Like I will say that like in some ways, the deep learning revolution is the worst thing that happened to causal inference. Because back in the good old days where like SVMs were all the rage, researchers mostly did feature engineering. They would sit and think about like clever ideas to represent the data. So when they pass it through like this simple SVM, they will get like good results.
And this has changed.
Yeah, and under that climate, like I would think it would be much easier for causal inference practitioners to sell what we do in causal inference, to think carefully about the input data what variables you select, at what time you select them, like the temporal relations between variables and how they interact. But then like along came deep learning, like, I don't know, the 2012 revolution, I don't know, like starting AlexNet and stuff. And the idea that you will just input as many raw data that you have and let the model figure it out in a much like more automated way really instilled that insight in people that like you can just take the data and you get something out of it. But there is no deep learning framework for causation. Like identification cannot be automated in such a way, or at least like fully automated in such a way.
Yeah,
it always requires metadata. And so when you tell, so people come with different, so collaborators come with different expectations, and when it hits them that they just like need to be more rigorous about their understanding of the underlying data generating processes, they are slightly disappointed. But then it's up to you to come and sweep them up and like encourage them and make them partners for this journey with you.
And also show them that, well, we have something that is more than just a regular machine learning model, right?
Exactly. So
to debias the effect, for instance, and so
exactly.
on.
And I think, like I said before, that like it's a bait and switch scheme, because like the underlying machinery, like under the hood, is regular regression model or machine learning models. But the good thing about causal inference software is that it makes the counterfactual prediction explicit, and so it allows you to conceptually grasp the difference between what the regression model would have done to what a counterfactual regression model does.
One of very exciting to general public use cases for machine learning is drug discovery. Mm-hmm. But when we think about the drug discovery process, sometimes maybe repurposing existing drugs might be a more efficient way to address certain diseases and so on. You worked with projects like this where you used causal machinery to repurpose existing drugs. Can you share a little bit with our audience about this experience and what those projects were about? What were the main challenges and main lessons from those projects?
Right. So, I mean, first of all, just to briefly explain, like drug discovery is the mission to find new drugs. Drug repurposing is about taking existing drugs and finding new uses for them. In some sense, that's pharma companies love it because it shortcuts the funnel that you usually have, like from discovering a molecule to testing it on animals to testing it on humans, like on varying different levels, that it's not toxic, that it's effective, and so on. And taking existing drugs really bypasses most of this process because it's already approved. So it's relatively safe, and you just need to prove it's efficient. It's efficient for the new disease. And there are many approaches you could do for drug repurposing, right? From like the molecular level, like the proteomics level, you could find molecules that bind to the target proteins and I don't know, like inhibit or excite its function. But more broadly, in the statistical sense, you can even shortcut this process of finding the molecular pathway, the mechanism itself, because you can take electronic health records or insurance claims data, and you can stratify on the people with some disease, and you can enumerate all the drugs they're taking, and then you can start comparing people who took the drug to people who didn't took the drug and see whether it improves the outcomes related to their disease, which is fairly simple conceptually. But how do you compare those who took the drug and those who didn't took the drug? Like, you need this comparison to not be biased, to be deconfounded, right? To isolate the effect of the drug itself. And this is where causal inference can help us to do this sort of modeling. So here in IBM, we set out to develop such a system, which takes like a configuration file written like in very high level, abstract level that physicians can even define, And then it goes through some strong black magic database querying of setting up the translating this configuration into, again, like translating into matrices of confounders and treatment assignment and outcomes, which is really a tremendous fit that the team did here, and they did excellent work on it. And then provide it into, let's say, the causal inference engine that will estimate the causal effects, the survival difference, or the cumulative incidence used under each drug regime. And to do that, it also needs to be done in a high throughput, because we, as I said, like we enumerate all the drugs patients might have taken. That can be hundreds of candidates. So there's like, first of all, like there's, in technical terms, there's some Docker machinery that needs to run those things in parallel in order to be efficient. But in the analysis, you also need to account for that later, because you have this multiplicity issue that you need to account for. And doing high throughput analysis, like you can no longer tailor the design for each specific drug, because each treatment outcome pair probably has like a slightly different structure, like a DAG around it. But you can't tailor a specific DAG to each outcome treatment pair because you have 100 of those. And so you need to have some trust that your data is rich enough in order to capture some of the internal state of patients. Like you have all their diagnostics, and you have all their tests, and you have all their previous prescriptions. And so it's not that far-fetched that those capture something about the inherent health status of those patients. And together with some variable selection, and together with some like proximal causal inference methodologies, you can gain slightly better trust on your estimates. But also, like, we are very down to earth. Like, we know that candidates that are being selected by the process, I mean, that this is a process that generates candidates, and candidates selected by the process are not directly translated into like good repurposing candidates. As in every observational analysis, like the results need to be triangulated from other sources in order to gain like more confidence in the evidence that these specific candidates are promising for the disease that they test on.
When we think about triangulation, do you believe that technology like large language models can be helpful in this? For instance, in searching large databases of scientific research and finding candidate articles again, right, that we could use in order to confront our hypothesis with the results.
Definitely. So I guess like large language models that are slightly more grounded into knowledge bases in some sense, but definitely, I mean, if I would have a large language model, trained on PubMed for like medical publications, and I find in my causal inference analysis that some drug with some active ingredient is beneficial, and then I go in and I query these large language models, and it tells me that there are some articles about that drug being effective in mice. So that's really strong evidence. I don't know if it's strong. I mean, evidence is a spectrum, but this like further reinforces your trust that this candidate might be promising. Then it should be moved further along for further testing to see if it can be really beneficial.
When talking about CausalLib and then about the system that you just described, you emphasize that it's important that those systems are efficient, that they are written in a certain way. We met yesterday for a dinner, and you told me that you believe in good code.
Yeah.
Why is that?
If you can trust the code,
You can trust the results. In some sense, the code
is God. Because it doesn't matter what you described in your methods section and like how well you describe it or not. Like, the code is very definitive about what it does and how it does it. And today's research is inseparable from coding. Software is inseparable from science in some sense, because you cannot do empirical research without statistics, without computation, without writing code. And in order to gain confidence in the conclusions, you need to have confidence in the methods. So you need to have confidence in code. And so testing code is like the most important thing. And I know like it's easier said than done, because like when we get to it, like people usually don't often like to test their code. Not just that it's important. I think like testing the code will allow you to design the code better in the first place. And if the code is designed better, if you can break it down into components, it means you can break down the question into components. And so those two are really tightly connected in some sense.
Those principles of modularity, is that something that you also used when designing CausalLib?
Of course. Yes, no, definitely. So designing CausalLib was first of all a lesson in figuring out how causal inference operates, knowing that you can estimate an effect, and you can also estimate counterfactual outcomes. It doesn't have to be the same necessarily, but counterfactual outcomes, like some models can estimate the average counterfactual outcomes, some estimate the individual level outcomes. Some models model the treatment, some models model the outcomes. And so figuring those out, like being able to draw a schematics around it, really deepens your understanding about causal methodology, like the methods themselves, the theory behind them. And then when you put it into code, it shines, like you see it.
What are the practical implications of building a modular system like this for causal inference specifically?
I think, and I can speak for CausalLib, but I think it allows two things. So first of all, if it's clean enough and it's simple enough, then people who want to learn causal inference methods can look at the code and learn. It also, which I think is one of the strengths CausalLib has, it allows you to scale very naturally and very easily, because using a logistic regression and using gradient boosting trees, or like a validation-based hyperparameter tuning model for gradient boosting trees, is a manner of like changing a single word in your code. I'm a very strong proponent of modeling the treatment. Like even if you want to end up with a heterogeneous outcome, heterogeneous effect estimation, and you need to model the outcome directly, it is still like very important to model the treatment regardless, to figure out how the treatment groups behaves, like how separable they are, how comparable they are, whether you have like overlap violations, that sorts of things. And so if you already model the treatment and you also like want to model the outcome, then like why not combine them? Why not do a doubly robust model, right? And I think CausalLib allows you to use those components and reuse those components quite easily, and do it again like in a way that scales, that allows you to create complex models very easily, and so you leave very little residual confounding bias. Again, it's up to the user to close the gap between like the causal estimate and the statistical estimate. But I think CausalLib allows you to close the gap between the statistical estimate and the statistical estimator, really like make them really tight and really close.
Today, you wear an archive t-shirt.
Yes.
Which I want to take a video of this, an additional one, so the viewers can see it, because I don't know if it's seen in other cameras. What dictated this choice today?
Yeah, so I knew it would be video recorded on top, or like it's a podcast, but today's podcasts are also video, I guess. Like why not make a statement? Like if it's already out there, like why not make use of it? That's like the efficient thing to do in some sense. And so preach what's important for you. And we spoke about open software, spoke about trustworthy open science. An archive in some way encompasses that.
What's important for you in the idea of open source, for open science and open software?
It's important because it can be checked and it can be assessed whether it is trustworthy. And if you wrote the paper in a good way, and if you wrote the code in a good way, then people can build on top of it much more easily, much more quicker, and we can move faster and we can discover new stuff much more quickly than we would have otherwise.
What are two books that changed your life?
I don't know. As a teen, I really liked to read, Douglas Adams and Kurt Vonnegut and Milan Kundera. I mean, those really impacted, really affected me. But if we're like slightly more on topic, so I think, can I have 3 books?
Yes.
All right. So first one will be Gödel Escher Bach by Douglas Hofstadter. Really like the most intelligent book I've ever read, I think. Read it during my bachelor's. It really made a mark. I remember concepts like being used so beautifully there, and it's written so nicely. It's written in such a smart way. It's really a delight to read. And so, especially like in these days and eras of like large language models, it's nice to reflect back on like the basic of language, like Chomsky's lemmas and such, and the science like behind it, not just like the billion parameter machinery that might be useful for it, the science behind it. A second book, which we just mentioned, between us, maybe the design of everyday things. So when I joined IBM, my mentor Ishai, he suggested me that book, and it's really an eye opener for anything you interact with in your everyday life.
Every interface you chat with, it's a bus station or a fridge or camera used.
So thoughtful about all the little details, or the fine detail, and all the broad aspects and specifics. And so that's a good book that can teach you about life, but it is also highly relevant if you write code, because it allows you, if you write code and if you do research, as again, like we said, those are really inseparable. So like it really allows you to organize your thought around like most basically like around the API of code, but also like how you organize research and how your research might interact with the world. Like even the basic structure of a research paper, introduction, methods, results, discussion, that's a design choice. It doesn't have to be like that.
And the third book?
Right. So I think the first book is slightly more directly related. So I think in the last like 10 years, I think I gained some very specific view about science and statistics and how to inference for that,
and how to do it properly and rigorously, and use for the inference for that.
And I picked it up little by little, fragments by fragments, reading books, hearing lectures, reading Twitter at the time. But then I encountered Richard McElreath's statistical rethinking. And he packs like 90% of the stuff I learned in a single book. And so it really resonated with me. I think it's an excellent book. Again, about rigorous, honest, thoughtful way to apply statistics, which puts science first and methodology second and analysis second, and breaks away from the usual machinery that we so automatically go for when we try to analyze data. I did some very some little consulting, also work with some hospitals, and researchers, their PIs, like they do experiment, they go and gather data. They spend millions of dollars gathering data, recruiting patients, recruiting healthy controls, taking measurements. Some of the measurements are done by doctors, by physicians. They bring them for days and they measure them. It's an entire operation, and they capture all this data. And when the time comes, they treat it like junk.
Like junk?
Yeah, they don't respect the data generating process. They do a t-test in some sense. Now, they were not taught anything better than that, but it's somehow, it's lazy, and it's ineffective. It's a waste of money to gather all that data, but not to analyze it properly. And it's also, I think it's disrespectful to the patients who gave their time and their hope in thinking like things might be better, like they will be the ones who will help make things better, and then like being used for a t-test, even though there are repeated binary measures in some sense. Right. So I think Richard's book is really pins the point on how to respect the underlying data and analyze it properly.
What would be your advice to people who would like to go into causal inference or causal machine learning research and or practice?
So I think the hardest part for like machine learning researchers going to causal inference is identification, is realizing that the kitchen sink approach we talked about before, where you just let the model figure it out, it does not exist. So that's like the first thing and the hardest thing to understand, because people with machine learning background, like they wouldn't, like it won't be very difficult for them to understand the algorithms and the models that do causal inference. But understanding that each problem has a structure that needs to be respected, that's like a slightly bigger jump they need to make. And unfortunately, as I said, like when I started learning causal inference, there weren't a lot of books and resources. But nowadays there are high-level stuff, low-level stuff, detailed stuff, less detailed stuff. Unfortunately, I'm not very proficient in them because I didn't grow up with them. But there are, and I really do think it will be slightly easier for them in that regard, and I'm very happy for that. We need more to jump aboard.
Who would you like to thank?
My family, of course. I mean, it's probably a cliche, but I don't know. First of all, like my parents, they instilled in me that like learning is important, and they put their money where their mouth is. Like literally, I don't know, when I was studying at the university, and I don't know if I needed some help, they provided help that like allowed me to focus on studying solely, just studying, and I'm grateful. It really did help me study better and understand more. Into the present, it's my partner and the mother of my kids. She's a bedrock. She's the most empathic and caring person, and she helps me with our everyday struggles. I mean, life is much more than just research, and she's there, and I'm thankful for her for that. But I guess like more professionally, like right, it's like the Maslow hierarchy, right? We talked about life, now we can talk about work. So I think professionally it will be probably Shai Shimoni. He's I mentioned him before. He was my mentor when I arrived at IBM. He is my manager now. He's a great person, very interesting person, and he taught me a lot. He taught me about the importance of coding. He taught me about design, and he really had an impact in how I perceive, I guess, like maybe research more generally.
Where can people learn more about you and your work?
With the internet being fractioning more and more, I opted for my own website recently. So it's at ehud.co, ehud.co. It has like all the other places, I mean, at the internet, like Twitter and Blue Sky and GitHub. It also has some teaching materials I upload for causal inference that might be interesting for people, and my blog. Probably most of it is on Medium, but some of it not, so that's also there.
What's your message for the Causal Python community?
Keep on rocking. I mean, it's been expanding so nicely, and the tooling is becoming more accessible and more trustworthy, and they're doing a great job, and I'm so happy to see. I'm so happy people can use it as a gateway to causality, and so just keep doing what they're doing.
Amazing. Ehud, thank you so much. That was a pleasure.
So grateful for having me. Thank you very much.
Thank you so much.